Hello students, so this is the lecture 2 of our non-composite course. So I have told you about the basic structure of the course in my last class, and so today we will take up the topic or the unit of energy storage, and I will be talking about uh, mixed transition metal oxides, and it's used in energy storage. Now, in today's world, we have new smartphones, electric vehicles, hybrid electric vehicles, and for that, there has been always a search for energy storage devices. And all the batteries, if you look into any electric vehicle or electric bicycle, you will see that the batteries are mainly, they will tell you it's made up of lithium ion battery. Okay. Now, this lithium ion battery has got some electrodes. Now, these electrodes are mainly made up of this mixed transition metal oxides. And new combinations of these mixed transition metal oxides are always searched for better energy storage and faster performance. Now, mainly you will see that cobalt based mixed transition metal oxides are used, and by that I mean that we have a cobalt oxide mainly, and this cobalt oxide is coupled with other metals. For example, you can have a zinc uh, cobalt oxide, you can have a nickel cobalt oxide, you can have a copper cobalt oxide, you can have a manganese cobalt oxide, and you can have an iron cobalt oxides. Okay, so all these materials have been are being in search, and our aim, what we have found out, is that instead of using an cobalt oxide, we would like to use manganese, right? So manganese. Now, the reason the manganese is used in place of copper is that it has got higher CS stands for specific capacity. I will tell you what it means, and it is more eco-friendly. Okay, these are the two reasons why manganese is being preferred, and we will be mainly focusing on your this material, zinc Mn2O4. Right. Now the synthesis process of this has been tried by many ways. For example, there has been something called sucrose assisted combustion process. And by this process, we have, or it has been found that we get an hierarchical porous. I will call it as ZMO. ZMO stands for zinc manganese oxide. So in short, we can write it as ZMO. Okay. So this has been found. The porous nature is very much useful in case of energy storage, because it actually eases the electrolyte, can easily pass through the pores. And talking about its performance, it has been found that this type of porous material has been found to give a specific capacitance of 416.96 farads per gram. This specific capacitance is actually the capacity to store energy, or in this case you can see that F stands for the farad, which is a charge storing capacity. So how much you can store energy, this is determined by this specific capacitance. In this case it has been found that it is 416.96 in 6 molar QAH solution. You need to have a solution for that, and scan rate of 5 millivolt per second. This has been the property of this material. Now, other techniques are also being used. For example, there has also been use of cadmium doped ZMO, and it has been developed by hydrothermal synthesis. Okay, and here the specific capacitance have been found to be 364 farads per gram in 2 molar KOH, and the scan rate was found to be 2 millivolt per second. Okay. Now, what we have done in our laboratory, one of our PhD students, Parameshwar Komo, who actually got his PhD thesis in 2018, he actually developed this ZMO, zinc manganese oxide, using sol-gel method, and he used PVA, which is a binding agent, plus urea, which is a combustion fuel, to make this ZMO. Okay. And interestingly, he got very nice results. For example, after getting now these sol-gel synthesis were made by using raw materials, zinc nitrate and manganese nitrate. So the zinc nitrate formula was Zn NO3 2 6 H2O is the aqueous part, and you had the manganese nitrate also, which is the same thing, NO3 O2 plus 4H2O, and PVN nitrate, PVN urea was almost already there. So by these raw materials, he made actually this ZMO, and after making the ZMO, he performed the XRE studies, and he found that the crystallite size, he actually found this zinc, the tetragonal phase of zinc manganese oxide were confirmed through XRE, and the crystallite size varied between 12 to 14 nanometers, which he actually obtained by first initially by the Scherer method, which you all know is D is equal to 0.9 lambda by beta cos theta. I think you already know what it means. This is the shape factor, this is the wavelength, which is 1.54 Armstrong for copper K alpha, which is the source, and this happens to be the Fulminant maxima of the peak. Okay, now another, by using the Williamson Hall method, which takes into consideration the lattice strain, and whose equation is beta cos theta is equal to 2 epsilon sine theta plus k lambda by d. This is the basic equation of the Williamson Hall. So it can be compared with y is equal to mx plus c. So this y here is beta cos theta, y is beta cos theta, x stands for 2 sine theta. So if we plot between y and x, we make a plot where you have beta cos theta in the y-axis and 2 sine theta in the x-axis. You will get a shape like this. So this is the intercept, which is k lambda by d, and the slope is actually the epsilon, which is the lattice strain. Okay. So the lattice strain actually came out to be 0.285. And interestingly, you can see that with increase in lattice strain, the crystallized size showed a decrease. This is due to the mechanical surface energy of the metastable nanoparticles. So just write down here the mechanical surface free energies of the metastable, this is important, metastable nanoparticles. So this strain is causing a decrease in the crystallite size. And lastly, to determine its performance, the cyclic voltammetry test was done, which is in short known as CVT. Basically, you get in current versus voltage diagram, and this is your 0. You vary the current from positive to negative, and you also get to find out the voltage. So you get a plot here, trained a plot like this. Okay, so the area inside the curve is actually the specific capacitance, and which is given as I integration ITV divided by 3.6 MV. Is M stands for the mass of the electrode, and V stands for the voltage. Okay. So the specific capacitance came out to be 603 mAh by G, milliamperes hour per gram, and this was very stable because it was also cycled in 1 molar lithium hydroxide solution, and 30 cycles were taken, and it was shown that the performance was quite stable. So the number of cycles was plotted, and this is the CV. So it was quite stable, around 600 mAh. Okay, so this was showing a much better performance than the previous counterparts made up of cobalt.